7.5 is all about analyzing quadratic graphs. Now, before we can analyze the graphs, I want to look at different transformations of these functions. So, I want to understand what a, h, and k do to any function. Now, as I've said I think it was a video in chapter 6, a is going to be a vertical stretch or a vertical compression. H is going to move left or right. It's going to move left if H is negative. No, it's going to move left if H is positive. It's going to move right if H is negative. So remember, it's always backward from what you might think. And then K moves up or down, and that is exactly what you would think: positive for up, subtraction for down. And so remembering these transformations, I want to look at a few functions that look like this, and I want to talk about their vertex, and I'm going to go ahead and write this down. Vertex is just h, comma, k. H, comma, k. And so if we have something written in this form, we're going to use h and k for our vertex. And once again, if h is negative here, it's positive here. If it's positive here, it's negative here. Okay, so once again, it's backward from what you might think. Okay, so let's look at an example of this. Y equals 3x minus 2 squared minus 5. So what transformations do we have? We have a vertical stretch of 3. We have a shift left or right, 2, and down 5. So this right 2, down 5, what I want to do is, if the blue is just the normal quadratic function, in other words, y equals x squared, that's the blue function. Okay, vertical stretch tells me it's going to be inside. It's going to be narrower, vertical stretch, because I'm stretching these things narrower. And then right 2, down 5. So 1, 2, 1, 2, 3, 4, 5. So it should be here, but it should also be narrower. So I've moved this vertex, this point at which a min or a max can occur, I've moved it right 2, down 5, because that's what this says. Right 2, down 5. So right 2, down 5. Then I applied this stretch. Now, once again though, I'm not accurately drawing this. I'm just drawing the vertex and then the basic idea. If I wanted to graph accurately, I could put 0 into my function, and whatever answer it gives me, that's what I need to put as my point on this line. Okay, so I'd have to be careful about that, but I'm just doing this to demonstrate the shift left and right, and that the vertical stretch makes it narrower. Okay, and I'm going to use an example from the book real quick. 2x minus 1 squared plus 3. 2x minus 1 squared plus 3. So if we have this function, okay, once again, blue will be the parent function, the original. Okay, so minus 1 means left or right 1. Well, it means right 1. Right 1. And this means up 3. So right 1, 1, 2, 3. So my vertex has shifted. Okay, now I can also account for this 2, which means it means slightly narrower. So it should be like this. Now, one other thing I want to bring to your attention is this piece called axis of symmetry. Axis of symmetry. It's the place where the left and the right are the same. So in the original function, the axis of symmetry is just x equals 0. It's just the y-axis. But when it shifts left, right, up, and down, the h piece, my left-right shift, tells me how the axis of symmetry shifts. So in this case, the vertex was 2, negative 5, right? Because I moved 2 and down. So right 2, down 5. The axis of symmetry is right here at 2. So axis of symmetry axis of symmetry is x equals 2. So this is our vertex, this is our axis of symmetry. We can always find axis of symmetry because it's just the x piece of the vertex. That's it. I don't even have to think about it. All I have to do is find my vertex and then write down my axis of symmetry. So in this case, the vertex is 1 and 3. So 1, 3 is the vertex. What about the axis of symmetry? Well, x equals 1. So I'm always going to have my vertex and axis of symmetry be linked because it has to go through that point. Now, both of the previous examples were written in this form. X minus h squared plus k. However, more often than not, our problems are going to be written like this. Ax squared plus bx plus c. So here the vertex is very easy to see. The vertex is hk. So over here I'll just put v h comma k. However, when we're given something like this, it becomes a little bit more difficult to see what that vertex is. But it turns out that if we look at the quadratic formula, minus 4ac all over 2a, it turns out that this negative b over 2a is the x piece of the vertex. So if I was going to follow this kind of logic, I would have negative b over 2a. Okay? Now, how do I find y if this is my x? I plug this thing back into my function. So if this answer, negative b over 2a, was 3, I would plug 3 in here and 3 in here, and it would give me a y value. So the way that we write that is by writing f of negative b over 2a. And that just means plug this thing that we found for x into x to find y. So why don't we look at an example of this? I'll just create a rather simple problem. Y equals 2x squared plus 8x minus 12. Okay, so in order for me to find x, I need negative b over 2a. Okay, well here's b. I'll just write it out. A is 2, b is 8, c is negative 12. So negative b, negative 8 over 2 times a, 2 times 2 in this case. So that's negative 8 over 4, which is negative 2. So that's my x piece. That's my x piece. So in other words, I have negative 2 comma something. I don't know what y is. I do this. So I have my x. How do I find y if I have x? I plug it in. Okay, I didn't really leave myself enough room here, so I'm just going to have to erase. So make sure that you pause and go back if you need to write that down. 2, but I'm going to put in negative 2 squared plus 8 times negative 2 minus 12. Okay, negative 2 squared is 4 times 2 is 8. And then 8 and negative 2 is negative 16 minus 12. Okay, well, what is 8 plus negative 16? That's negative 8 minus 12. Negative 8 minus 12 is negative 20. So my y value is negative 20. So in this simple problem that I made here, I did negative b over 2 times a, and then I plugged it in, and I got negative 2 for my x and negative 20 for my y. Now, this is the vertex, but what about axis of symmetry? Remember what I said a few minutes ago? Axis of symmetry is just the x value. X equals negative 2. So my axis of symmetry is x equals negative 2. Now, there's one other thing that we've kind of overlooked in looking at this, is that these vertexes are actually maximums or minimums. And the way that we determine if it's a maximum or a minimum is, if the graph opens upward, then this would be a minimum. If the graph opens downward, this would be a maximum. And so if it is positive here, it opens up. So this is if A is positive. Positive A gives us a minimum. Negative A gives us a maximum. Okay? And so what we're trying to do is we're looking for negative b over 2a, negative b over 2a, getting our piece, then plugging it back in. This, once again, if we're given something like this, it's going to work every time. Okay? If I have something like this, I don't need to do that because HK is right there. I don't need to spend the time to worry about it. I just need to plug H and K in. So one good thing that quadratic functions are useful for is maximization of area or height or things like that. So I do want to look at two examples really quickly of how we could use something like this. So if I have a fence, okay, and I'm going to connect a koi pond to this fence, and the koi pond is made out of stone, but I only have 24 feet of the stone. Okay, I only have 24 feet. Now, what do I know about the sides here? I know the backside doesn't count as part of my 24 because I already have a stone fence here, stone wall, whatever. If I call this W and this W and this L, how is L going to be related to W and this 24? Well, if I have 24 as my total, then this side here would be 24 minus the other two sides. So that'd be 24 minus 2W. Okay, but not only do I want to figure out how much each side is, I want the maximum amount of area that this space can cover. So I want the maximum amount of area for my 24 feet going this way and this way. So I want to know, should I use 6, 6, and 12? Or maybe I should use 7, 7, and 10. Or maybe some crazy decimal. And so what I need to do is I need to find area. But what's area of a rectangle? Length times width. So length times width. And so I now have 24 minus 2W times W. Okay, well, what does this give me? That would give me, now I'll do that in a second. 24W minus 2W squared. But I want to write this in descending order just because that's my habit. Okay, so you can see that I've now created my function. So we'll call this f of, f of w. F of w. Okay, so f of w is equal to negative 2w squared plus 24w. Now, what I want to do is I want to find that maximum minimum point. So I want to find either that or that. Now, do I know that this function opens upward or opens downward? Well, it has a negative in front of the x squared piece, a negative a. So that means that it's going to open downward. So I don't need this. I know now that it's going to be a maximum function. Okay, so now I just need to find this vertex. Well, how do I find vertex with this kind of thing? Negative b over 2a. Okay, well, let's plug those in. So in this case, that's going to be negative 24 over 2 times negative 2. Negative 24 over negative 4 is 6. So we now have 6. That's the first piece. Second piece is finding the y value, or the area, the function value of w when w is 6. So let's plug in 6. So we have negative 2 times 6 squared plus 24 times 6. Okay, 6 squared is 36 times negative 2 is negative 72. 25 times 6, 6 quarters would be 150 or $1.50, right? So I take away 1, and that should give me 144. And it just so happens this is half of that, so positive 72. We should get 6 positive 72. But how do we take this value, and translate that into something useful for this problem? What is 6? 6 is w. So that means the width should be 6. And if the width is 6, what is the length? Well, 24 minus 12 is 12. Okay, now what is the area of the koi pond for this person's backyard? 72 feet. 672. So it gives us both the dimension and the area. And so that's one example of how this can be useful. Now we're going to do an example of height, maximizing height. So like a rocket is launched into the air, and we want to know what's the maximum height that it reaches. So I've got this rocket, and I launch it into the air, and it is determined that the rocket follows this function. Negative 16t squared plus 100t plus 20. Okay, so I need to follow, once again, I need to follow that same idea. I have to find the vertex, because that's where this maximum is going to occur. Once again, how did I know it was a maximum? Negative a. So I have 100 over negative 16. Sorry, I forgot the 2. So 100 over negative 100, negative b over 2 times a. I should just say it every time. So 102 can reduce, and that would be negative 50 over negative 16. And this negatives reduce to become positive. These can reduce as well to 25 over 8. And I believe that is 3.125 as a decimal. And we're going to use that. So this is my x value, 3.125. 5. We need to find how high it goes. Now, what is 3.125? I didn't really specify earlier what the t was. The t is the time in which it took for this thing to occur. So this thing right here is actually acceleration due to gravity, is this idea. And then this is a physics problem that uses velocity and initial height and those kinds of things to determine the maximum height or how long things are in the air, stuff like that. And so this tells me how many seconds it took to get to its maximum height. So I have the seconds. Now I need to plug those in to find the total time. So if you need to catch up on any of this, go ahead and pause the video to write that down. I'm going to erase it so I can have some room. Okay, so I'm going to plug in the 3.125, that's negative 16, 3.125 squared plus 100 times 3.125 plus 20. Now this one is easy math to do. That's 312.5 plus 20. This is not so easy, so I'm going to cheat. Okay, the book did it a slightly different way than me, so I'm going to have to really quickly in my head do some math. I'm going to say 3 times 3 is 9. I'm going to say that this is roughly 10.5, and we'll go with that. Okay, so now I need to multiply these two things together. Well, 10 times 16 is 160. 0.5 times 16 is 8. So that's negative 168 plus 332.5. Right, I just added these two together. Now this minus this, let's see. 0.5 minus 0 is 0.5. 12 minus 8 is 4. That's a 2 now. 12 minus 6 is 6. And 2 minus 1 is 1. So this is approximately 164.5. Now, my answer is different from the book's answer because I rounded here. I think the actual value here must be closer to 10. But anyway, this would be the height of the rocket at its maximum value. So we have the time and the height. And so you can see that this can be used for a lot of things that are shaped like this. So anytime you launch a rocket, it's going to go up and then come back down. And so you can model that as time over height. And it can also be modeled linearly if you want to talk about distance. So you could actually model the exact same thing, and you could ask yourself, well, how far linearly did my rocket go? And as time goes by, how far it goes would maybe look something like that, because it's traveling faster and then it kind of slows down. So there's many different ways that you can look at this, but quadratic functions can be used quite nicely in analyzing, maximizing area, maximizing height, and those type of functions.